Okay, so let's get into the concept of a series. All right, so in this setup, what we have is a sequence of numbers. We always have a sequence of numbers, xn, 1 to infinity, maybe it's an, 1 to infinity, use whichever notation you'd like. And we call this thing that looks like a summation of n going, typically starting at 1, but not necessarily, 1 to infinity of xn, a series. Okay, the distinctive feature is, of course, that we have this infinity at the top. And it is a formal object. So what does it mean when we say that something is a formal object? Well, formal proofs are proofs that are formal in the sense that they're rigorous, that every step is can be followed step by step, and there's full kind of logical continuity between statements to prove some sort of statement. But a formal object is something else. By a formal object, what we mean is that this thing, well, it's not an object that we've shown its mathematical existence. Maybe it exists, maybe it's not. We could have, and there are just ways we use it, right? And specifically for series, well, maybe this thing does not diverge, so there is no number or no vector or no matrix or no other object that we can mathematically manipulate that is this. And maybe sometimes it does converge to a number, but we'll get to that in a second. So then hence we start by just saying that it's a formal object. Okay, so to see what we mean by that, we have to speak about the partial sums. And they are not formal objects, they are real objects. So real in the sense that they're concrete mathematical expressions that follow all of the rules that we have learned within the field of real numbers, for example. So S sub k is just going to be the sum n going 1 to k of x sub n. Okay. Or if you'd like this with a summation notation to open it up, it's x1 plus x2 plus xn. Okay. Now that's a finite sum. N might be very big. Maybe it's 5,000. Maybe it's a million. We don't know. But there's still rules on how to manipulate this, and we could follow those rules fully. So these are the partial sums. And since we have these partial sums, we also have the sequence. We have the sequence of partial sums. S, K, K going 1 to infinity. So this sequence is created by the sequence xn, right? Because if I know the first 15 elements of xn, I know what the 15th element of sk is. It's the sum of those guys. And if sk, k going 1 to infinity, converges, we say the series converges. That's what a converging series is. That's what it means when the series converges. And then this object, which was just a formal object before, this thing actually means the limit n to infinity. Let me put here k to infinity of sk. Okay. Or if you would like, you could have just written the limit. What am I doing? The limit k to infinity of the sum n going 1 to k of xn. Right? So this series then just means the limit. So in a sense, a series, a convergent series, is nothing but a convergent sequence, only that the elements of the sequence are partial sums. And let's continue. If Sk, k going 1 to infinity, diverges, so sequences are either convergent or divergent. And if the sequence of partial sum diverges, we say the series diverges. And this n going 1 to infinity of xn does not have meaning as a number. Okay, we can still use this notation. It just means that it does not have meaning. It's kind of like saying, if you take just as a side, if we would have had the sequence u sub n, n going 1 to infinity, where u of n is n squared, um, we, without putting further notation, saying limit n to infinity of u sub n, this is also just a formal object. In fact, while we didn't define it properly in the course, we could have also said that this equals infinity, and then it's an object that has further meaning, because infinity, that just means that this is a sequence that diverges to infinity. Okay, but we didn't speak about divergence to infinity. So what I want to say is that this thing, you could still use it. It does not imply that the limit of the partial sums exists. You have to say if the series converges or diverges. Okay, so series either, just like a sequence, either converges or diverges. A series, which is a special case of a sequence, also converges or diverges. So the thing is that for most series, we won't be lucky enough to have a nice, simple expression for the value or the sum of the series, for the actual limit of the series, or the limit of the partial sums. Sometimes we just call it the sum of the series when the series converges, but we'll just be able to say if it converges or diverges. However, geometric series, which play a central role, are special, and they have an explicit expression. And a few other very special series have explicit expressions, but actually many constants in mathematics can be defined through series. I mean, even pi, for example. Uh, that can be one way of defining pi. So let R, here's proposition 2.55 in the book, let R be an element in negative 1, 1, then the geometric series, and there are a few versions of this one. I like this one, n going 0 to infinity. Rn converges. Okay, so R is strictly greater than negative 1 and strictly less than positive 1. Okay, converges, and sum n 0 to infinity Rn equals 1 over 1 minus R. Okay. Oh, if we would have started with a 1, you see that version also, then you can show that it would have been an R divided by 1 minus R. But don't worry about that. Okay, so proof sketch. Okay, so most of the kind of things one you need to do in the proof here is to actually show with algebra, because you're only speaking about finite sums. Okay, you want to show that the sum of n going 0 to k of R n is going to be this expression. It's 1 minus r to the power k plus 1 divided by 1 minus r. And that is for all r not equaling 1. Okay. I mean, you can also show that for r equals 1, this is for r equals 1, this would have just been k plus 1, right? You just have capital K plus 1 terms there. This expression is not defined for r equals 1 because you're dividing by 0. But all that story about r equals 1 doesn't matter because we could just, for the purpose of this statement, we could just stay within the confines of the assumptions of the proposition, and that r is in the open interval -1, 1. Right? Now, this is sometimes people would see this and say, oh, that's a geometric series, but that's loose. That's not a geometric series. That's a geometric sum. This is a finite sum, and it has nothing to do with convergence or divergence. In fact, one way to show it is you just kind of take out the first term. So you'll have an x, or maybe multiply by r and kind of get an expression for the partial sum sk and the partial sum sk plus 1, for example, and work that out and then just do 2 or 3 steps of algebra. That's not so hard. It's a fun thing to do when you're waiting on the bus stop and you have something to write on. Okay, but you have this. So in this case, we just have that the partial sums sk actually have an explicit algebraic expression. We're not often so lucky to have that. And here it is. Okay, it's that. And now the second part is with basics of sequences. Right, so showing the limits of the sequence in one or several ways. You can even just go by the definition of a limit. Then you can show that limit n to infinity of the expression 1 minus r to the power k plus 1 divided by 1 minus r, well, this thing just vanishes and you get a 1 divided by 1 minus r. Okay, you can use the fact that arithmetic operations carry through sequences, so you carry out this limit separately and this limit separately. Well, all of this, say, is just one number, and then you divide by that number and you do this. And basically, your important thing is to show that the limit of some number whose absolute value is strictly less than 1 to the power k goes to goes to 0. And that's why you get this 1 over 1 minus r. Let me just fix this to, I'll put a k here. Okay, so we want this k to be this k. Okay, so that's it. And pretty soon we'll show that for r that's not in this range, the series actually diverges, right? So this statement on its own right does not say that the series at r equals 7. Okay, when I say the series r equals 7, we have here a family of series. We don't have one series, we have a continuum series for all r, but it does not say that that series diverges. Okay. Okay. So the next concept we have is a Cauchy series. Now, we know what a Cauchy sequence is. A Cauchy sequence, I'll say it in words, I won't write it, is a sequence of numbers such that for every epsilon, there exists an capital M, such that when you go for indices beyond that capital M, say K and L, the difference between XK and XL in absolute value is less than epsilon. And we've shown that on the real line, Cauchy sequences are convergent sequences, and convergent sequences are Cauchy sequences. So the Cauchy definition holds for convergence. We are now going to do an analogous thing for series, and we'll see that it's quite useful for series. So definition 2.5.2 in the book is a series. Let's write the series n1 to infinity of xn is, and we're just going to say the series is Cauchy. Okay, or you can call it a Cauchy series, but sometimes you just say, hey, that series is Cauchy. But it's also going to mean that it's convergent. Okay. If the sequence of partial sums is a Cauchy sequence. Okay. And because, as I've now just said, Cauchy sequence is a convergent sequence, and a convergent sequence is a Cauchy sequence, we have that a Cauchy series is convergent, and a convergent series is a Cauchy series. Okay, so a series is convergent if and only if it's Cauchy. Still, we can now do just a bit of manipulation and get what's quite useful, and we call that a proposition here. So proposition 2.5.8 in the book, and that's often called the Cauchy criterion. Okay, so it's going to be a criterion on the series that effectively sees, or doesn't effectively sees, that the series satisfies the Cauchy definition that the sequence of partial sums is a Cauchy sequence, and it's going to be a criterion for convergence. Because a lot of what we're going to do in this whole series little unit is deal with criteria and tests for convergence or for showing divergence of series. So the series, let's write it again, n1 to infinity xn is Cauchy, and that by this thing, it also means it's convergent if and only if. So this is both a criterion for convergence and divergence because it's if and only if there exists some m, natural number m, such that for all n greater or equal than m, and for all k greater than that n, that little n, this thing, the absolute value of I going from n plus 1 to k of x sub I, the absolute value of this summation is less than epsilon. Okay. So the proof is something you can just do yourself, write it. I'll just say it in words. All we did for the proof of this thing is we said, okay, let's look at the sequence of partial sums. The series is Cauchy if for every sk, if the Cauchy definition of a Cauchy sequence holds, if sk minus sl is less than epsilon. But we're not going to use k and l. We're going to use here n and k. So it's going to, and we're going to assume that k is greater than n. So we're going to write sk minus sn. Now this guy is a summation from 1 to k. This guy is a summation from 1 to n. What we're left with, if we do the subtraction, is a summation from n plus 1 to k, okay, less than epsilon. Okay, so the Cauchy criterion, this proposition is nothing but an adaptation of the definition of a Cauchy sequence, but it also uses the fact that Cauchy sequences are convergent. Okay, and convergent sequences are Cauchy sequences. So hence, this series, the sequence of partial sums, the series whose convergence is determined by the convergence of sequence of partial sums, will hold if and only if, back to our criterion. Let me now kind of clean up what we had in the criterion. You know what? I'll just do this and erase this guy. If this holds. Oops. That's artistic, but that's not what we really wanted. Neither is that. I think what we want is this. I going from n plus 1 to k. Okay. Now, I'll just also say that you might see this sometimes in a different way. Instead of saying here that there exists some capital M with all the little n's greater than capital M and all the little k's greater than that n, we could have said, let's just fix that n and then go to some p. And p would have been just the difference. So we could have, let me write that version of it. You could say for all p greater or equal than 1, and then here we would have written n plus p, right? So this is the same thing. This version of this statement is the same thing, only now I've just shifted the indexing, and then I don't have to have that p here also depends on n. So it's a different way of writing it. That's all. Okay. So that can be done as well. That's all what I want to say. But we'll stick with the first way of writing it with the k. All right. So that's the Cauchy criterion, and it's useful for as a basis for quite a few of the results we have in series, and as a basis for them. Okay. And here is now, sometimes this is called a criterion for it's not a sufficient criterion for convergence, but it's a necessary criterion for convergence. So here's this proposition. And the proposition is that the series n1 to infinity xn, if it converges, then limit n to infinity of the individual terms, xn, of the sequence of terms, must be 0. So you can't have a series that has the limit of the individual terms being 0, not being 0, and the series will converge. So what I just said is the contrapositive of this statement. So let me write it. Now this could have been the proposition, or we could have put the contrapositive in the proposition. Let me do the contrapositive in the proposition, and this is called the contrapositive. Okay, so contrapositive, just a bit of a side statement, just in case that's not clear to you. If A implies B, the contrapositive of that is not B implies not A. So this statement and this statement, they are logically equivalent. If A implies B, then not B is not A. Don't get confused by thinking that if A implies B, then not A, sorry, implies not B. This, in general, is a logical error, to think that if A implies B, then not A implies not B. However, by switching the direction here, right, and I could have made it maybe just a bit nicer for you, instead, different way to kind of write this contrapositive, I would have written I could have said a not B here, just put in, I'm going to take this guy and I'm going to say not B implies not A. I'm keeping A and B in their respective physical positions on the paper. Anyway, that was a bit of a digression to some basic logic to contrapositive. So what's the contrapositive of this? So the contrapositive means that if limit, or if, let's say it like that, if xn diverges, or limit n to infinity of xn equals L, with L not equaling 0, then the series n1 to infinity of xn diverges. Okay, that's the point positive, because this statement here, this is our B if you would like. Okay, this statement says that xn has a limit and that limit is 0. So if you want to say what is not B is, well, there are two ways that B cannot hold. It can be that xn just diverges. When I said xn diverges, I mean the series xn n1 to infinity diverges. Or maybe it converges, but its limit is just not 0. Then not A. What's not A? Well, the not of the series converging, maybe I call this a series. I should call this sequence in my words, sorry. The series of not this converging is this diverging. Okay, so there's different ways to show this thing, but with the Cauchy criterion, we have a nice little proof for it. And let epsilon greater than 0. So now we actually want to show a limit, right? We actually want to show a limit. We're going to use the definition of a limit of a sequence. Okay. So from this proposition, the Cauchy criterion, since the series n1 to infinity of xn converges, okay, it is Cauchy. Hence, there exists an M, right? Cauchy said that there existed an M. Hence, there exists an M, such that for all n greater than that M, the summation there was also, and for all k, we had that this tail of the series greater between n plus 1 and k would the sum of this things would be less than epsilon, absolute value. Now, let's just pick k to be the next one after n. So k is going to be n plus 1. So since it's Cauchy, that's also going to hold. So I'm not gonna pick a k anymore. K will just be my n plus 1. So we'll say I from n plus 1 to n plus 1. So there's only one summoned in this sum, and that's x sub n plus 1. Okay. And this is going to be less than epsilon. That was the Cauchy series. Well, this is nothing but the absolute value of xn plus 1. Or if you would like, you can say that's the absolute value of xn plus 1 minus 0. So hence, for all n greater or equal than n plus 1, xn minus 0 is less than epsilon. And that means that the sequence xn has a limit 0. Okay. So for the series to converge, we must have that the general term, the sequence, the sequence that drives the series converges to 0. All right, so now with this result, we can complete the picture on the geometric series. So let's again go back to the geometric series, n going 1 to infinity of r to the power n. And we had that the geometric series converges if r is in absolute value less than 1, right? So converges if the absolute value of r is less than 1. And now let's show the claim. Let's show it diverges if r in absolute value is greater or equal than 1. Okay. So you can look here at R if you would like. and this is 0. And for r between +1 and -1, the series converges. Whoops. Otherwise, it diverges. And this kind of is called it's not kind of, it's called the radius of convergence. We're not going to do in this unit something called power series. You might have it later in the course or in some level. So the geometric series plays a key role there, and it plays a key role in series in general. But the radius of convergence of it, when you look at it as a parameter in terms of r, is 1. So it converges between -1 and +1. So let's use this theorem to show that it diverges, right? So let's look at geometric series with r greater or equal than 1 in absolute value. So take some n 1 to infinity Rn with r in absolute value greater or equal than 1. Okay. So if it was to converge, we would have had to have that the sequence r to the power n converges to 0, but we show that Rn cannot have limit 0 in this case. Okay, and the way to show this is you could look at Rn minus 0, and that's just r to the power n, and that is absolute value of r to the power n, and that is greater or equal than 1 to the power n, because r in absolute value is greater than 1, and that's 1. So it's not the case that for every epsilon there exists an m such that all n's greater than that m put us less than epsilon. In particular, with epsilon equaling 1, that doesn't hold. So this sequence cannot have the limit 0, and by this proposition, the geometric series diverges. Okay, so that is that claim. However, something's a bit deceiving when we consider the geometric series, because it makes us feel that, if you look at the family of all geometric series, the ones with R in the good range, like that, converge, meaning the ones where the sequence Rn converges. Now, actually, when R is specifically 1, the sequence Rn, r to the power n, still converges. It's just a constant sequence 1. Okay. That's not the case when r equals -1, because that's an alternating sequence. But still, we don't get kind of a satisfactory answer, because we might think, oh, let's try to prove the direction that any series that has its general term xn going to 0 will also converge. Okay, but this direction here is not correct, right? So, and here is a proof. So claim there exists a series some n1 to infinity xn with limit with, let's say that, with limit n to infinity of xn equaling 0, that diverges. So the series still diverges. Proof the harmonic series. So sum n1 to infinity 1 on n diverges. So let me show you this. Let's see why the harmonic series diverges. Okay, so the harmonic series is a series of 1 plus a half plus a third plus a quarter plus a fifth and so on. So you're adding smaller and smaller things, but those things don't get small so quickly. They don't get as small as these things get small when r is less than 1 in absolute value. Okay, they don't get exponentially fast small. Yeah, quite slowly small. You don't have to get exponentially fast small, whatever that means to you if you'd like, to converge, but this series diverges. Okay. And by the way, harmonic series are in general important. So the harmonic sum, we're not doing this in the course, but you can see elsewhere that n equaling 1 to k on 1 of k is something of the order of log k plus some constant called Euler's gamma plus something a little over 1, something that vanishes. But in general, this series grows very, very slowly because you're adding terms and those terms are getting smaller and smaller, so it grows kind of a logarithmically. But again, that's not our main point. But let's argue why the harmonic series diverges. So let's look at the sequence of partial sums. So what I'm going to do is I'll look at the first partial sum, that's S1, and that's just 1. Let's look at the second partial sum, S2, and that's 1 plus a half. And let's look at I'm going to skip the third one. I'll just write like a little S3 here. I'll look at the fourth one, and that's 1 plus a half plus a third plus a quarter. And I'll also, I won't really look at the fifth one or the sixth one or the seventh one or the eighth one. Sorry, I will look at the eighth one. So that's 1 plus a half plus a third plus a quarter plus a fifth plus a sixth plus a seventh plus an eighth. And I'll continue in this way that I'll skip the 9th and skip the 10th and skip the 11th, skip the 12th, skip the 13th, skip the 14th, skip the 15th, and then look at the 16th one. So I'm only looking at powers at the subsequence of the sequence of partial sums, but I'm looking at the subsequence 2 to the power with indices 2 to the power 0, 2 to the power k, when k equals 1, sorry, k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, etc. So this one is just like this one plus another kind of big thing that goes from 1/9 up to 1/16, right? And what's instructive to do here is to actually group the terms like this. So look, this half is just this half, that's there. This third and a quarter, that's kind of your second group of terms that puts you up to kind of in terms of powers of 2, it puts you up to the fourth term. And then you have this group. And, if you would have looked at the 16th, you would have had the same kind of groups as you would have had before. You would have had a 1 plus, 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 plus. You would have had these groups. So we can break up the the powers of 2 elements of the sequence to these kind of quite orderly groups. And without too much hassle, you can actually verify that for general k, if you were to look at the element in the sequence of partial sums, the 2 to the power kth element, then what you would get is, of course, the 1. That's your first term of the sequence. And then you're going to get I going 1 to k, you're going to get k terms. So let's see, there's k equals 1, k equals 2, there's 2, k equals 3, there's 1, 2, 3, k equals 4, there's 1, 2, 3, 4. So you get k terms. And you can represent each of these k terms. It's a bit ugly, but not the ugliest thing in the world. There are a few things in the world that are a bit uglier. So m equals 2 to the power I minus 1 plus 1 to the power 2 to the power I of m. So each one of these guys is one of these guys, right? Or for any k, right? So for example, when I equals 1, you get, if you look at this thing, let's just look here. When I equals 1, it's 2 to the power 1 minus 1 plus 1. That's 2 to the power 0 plus 1. And we're going from 2 till 2 to the power 1 till 2. It's just this. When I equals 2, it's always a third plus a fourth. When I equals 3, it's always a fifth plus a 6 plus a 7 plus an 8, etc., etc. So it's not the hardest thing in the world to see that this thing holds. And now what we're going to do is we're going to find a lower bound for each of these guys. Okay, so let's notice that a third plus a quarter is greater or equal, well, it's greater if we'd like, than a quarter plus a quarter. So, and that's a half. And let's look at this guy. Let's look at a fifth plus a sixth plus a seventh plus an eighth is greater or equal than eighth plus an eighth plus an eighth plus an eighth. So we've lower bounded each of those terms, and that's 4/8. That's a half. So each of these guys has a lower bound of a half. If you want to see this slightly more formally for the general term, then let's argue that the summation of m going from 2 to the power k plus 1, sorry, mistake, 2 to the power k minus 1 plus 1 down here, all the way to the power 2k on 1 on m. So that's this term. By the way, this was a typo here. This shouldn't be an m. It should be a 1 on m. Okay. When I wrote this initially, I had a typo. It should be a 1 on m. Okay. 1 on m is greater than equal than the summation of m equals 2 to the power k minus 1 plus 1 all the way to the power 2k on 1 on 2k, 2 to the power k. Why? Because all of these terms are less than or equal than that last 2 to the power k. You see, that's the 4 was a 2 to the power k here, and that's a lower bounding. The 8 was a 2 to the power k, and that's a lower bounding, etc. So now there's questions of how many terms are in the summation. So in general, when you sum m equals a to b of some ui, you have b minus a plus 1 terms. Okay, so the number of terms in our specific case is 2 to the power k minus 2 to the power k minus 1 minus 1 plus 1. So I'll just take it and leave that terms, or you can factor out 2 to the power k minus 1, 2 minus 1 terms. So there's 2 to the power k minus 1 terms, and they're all the same. They're all 2 to the power k. You see, this lower bounding, the idea of the lower bounding is we no longer depend on m here. It's just 2 to the power k. So that is just 2 to the power k minus 1 terms times 1 over 2 to the k, and that's, of course, a half. Okay, so this is an argument that shows that each of these guys is lower bounded by a half. So the nice thing that we did here is we represent an inequality for the 2 to the power kth partial sum of the harmonic series, and we have shown that it is greater or equal than the 1 that we have here. And by lower bounding all of these to halves, I'll say plus some I going 1 to k of a half, or just that's 1 plus k over 2. Okay. So the subsequence of partial sums with indices 2 to the power k is unbounded, because you see, for any bound that you give me, you're going to get greater and greater, because I can always kind of reach that lower bound. And hence, s to the power k, the sequence itself, because it's, and hence, okay, if you want hence the subsequence, hence s2 to the power k, k going 1 to infinity, diverges. And because the subsequence diverges, hence the sequence of partial sums, sk, k1 to infinity, diverges. And because the sequence of partial sums diverges, the series diverges. So what we've seen is that the harmonic series diverges. And again, it's kind of interesting to know that it diverges super, 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 super slowly. So if you were to compute the harmonic series as much as you'd like, you're not going to grow very far. Even if you can compute if you want to grow up to about 100, if you want to get this sum to get up to about 100, you need like something in the order of 10 to the 50 or 10 to the 40 terms. That's a lot of terms because you're adding up very small things. But still, it diverges. So we've seen that there's no way to actually show this other side of the theorem because it's not going to be true. It's not that convergent series are characterized by series that have converging sequences or general converging terms of the series that we're summing up. Okay, let's continue, and we'll continue with a concept called absolute convergence. So here I've just stated proposition 2.5.13, and it's read as follows. So if xn is non-negative for all n, then the series converges if and only if the sequence of partial sums is bounded above. Okay, and the argument is very simple. It's simply that the partial sum, that's the sum going from n1 to k of x sub k, is monotone increasing if xn is greater than 0, greater or equal than 0 for all n. Okay, because you're only adding more terms. All right. And in such a case, we've already proven with the monotone convergence theorem that for monotone sequences, bounded is equivalent to convergence, and indeed the supremum of this set of partial sums that we're going to get for every k is going to be the sum of the series. So for such series, so when xn is greater than or equal to 0 for all n, we always have that the partial sum for any k is bounded above by the value of the series. Okay. Yeah. Now this is by the way, this is true. This is also true if the series diverges. This will happen when the sequence is not bounded above. But then if you allow this thing, if you interpret it as infinity, if you would say that when the series diverges, a formal object like that equals infinity, this inequality would still hold. So all this just motivates the definition of absolute convergence, and here it is. So definition 2.5.14 in the book if you would like. So a series, and here's our series, sum n going 1 to infinity of xn, and we say converges absolutely if a different series, potentially a different series, if the series, here is a series we're speaking about, n going 1 to infinity of the absolute values converges. So we already know what the definition of convergence of a series is. That means that convergence of the sequence of partial sums um, is converging. And you're now given some series like this. Okay. And we say that series converges absolutely if this other series converges. Now, this other series, well, what's the difference? Of course, if all of the xn's are non-negative, as in the precondition of this proposition, then both of these series are the same. So then every series that converges absolutely. But perhaps the series has some negative terms, and then this series down here is different, right? Because this series is just has non-negative terms, and the partial sums are monotonic increasing. Okay, so that's what we say when a series converges absolutely. Now we also say in the same definition, if a series converges, but does not converge absolutely, then it is conditionally convergent. Okay, so if a series is conditionally convergent, it's still convergent, but then when you get from it the other series, a series of the absolute values of the elements, then it's not, and if that series does not converge, then it's conditionally convergent. Okay. So for a series to be conditionally convergent, you must have some negative terms, right? Because otherwise, if the series converges, the series of absolute values converge. But not all series with negative terms are conditionally convergent. Now, the result that's of interest is proposition, and the number for that is 2.5.15, and that is if the series, and let's just write the series, n going from 1 to infinity of xn converges absolutely, then it converges. Okay, so you're given some series. If you can show that it converges absolutely, what does it mean that it converges absolutely? It means that you provide on the side a different series, and that series is going to be n1 to infinity of absolute value of xn, and you've shown that this is finite, meaning that it exists. Okay, you can write it like that, or just to say that it converges. So this one converges, hence this one also converges. Okay, that's this theorem. And this goes hand in hand with this definition, right? Because then if the well, you can have series where this does not hold and this still does hold. Okay, and I'll show you an example as well. Okay, so let's look at the proof of this theorem. So first of all, we'll say convergent is if and only if it's a Cauchy series, right? If the Cauchy criterion holds, right? So let's assume that now that the series converges absolutely. So what does it mean that the series converges absolutely? It doesn't mean that it does not mean that the Cauchy criterion holds for this thing. It means that the Cauchy criterion holds for this thing, right? So then, because the series, so assume that, okay, sorry, I had to stop the recording. Let's just continue with the proof. So just get to it right back again here. Okay, so we are proving that if the series converges absolutely, then it converges. It converges. So assume the series converges absolutely. So that means that this series, the series of absolute values, converges, and then that means that it's Cauchy. Okay. So hence, for all epsilon greater than 0, there exists a capital M such that for all k greater than that capital M and for all n greater than that k, this Cauchy criterion holds. I going 1 to k plus 1 up to n of the absolute values of the xi, this sum of the series of the kind of between k plus 1 and n of the tail of the series is less than epsilon, right? So this is a Cauchy criterion applied to the series of absolute values because we assume that the series of absolute values converges, right? And that's what it means. So the series itself, the original one, is conditionally convergent. Okay. Now, of course, we don't need that external absolute value because this finite summation here is just summing up non-negative numbers. So we can just write I equals k plus 1 up to n of the absolute value of xi. Okay. Now, from this step, if we go with the triangle inequality here, but we go left, so meaning we go to the other side, then this is going to be the sum of I going from k plus 1 to n of xi all in absolute value, right? So this was a triangle inequality. And what does this show us? Well, then we see that hence the original series, the series n1 to infinity of xn is a Cauchy series. So it satisfies the Cauchy criterion, and hence it converges. Okay, so that's it. That was this proof. And just to close this small little subsection about absolute convergence and conditional convergence, I'll just say, and we'll see this just a bit later, that the series, this one, which looks kind of like the harmonic series, n going 1 to infinity on with n's in the denominator, but with changing signs. So we're talking about -1 plus half minus a third plus a quarter, etc., converges. Okay, we can show that a bit later that this series converges. Now, what does this mean? Well, let's see. Is it absolutely convergent? Convergent? No, but does not converge absolutely, right? Because when you look at the series sum n going 1 to infinity of -1 to the power n over n, put that in absolute value, you just get the series n1 to infinity on 1 on n, which is the harmonic series, and it diverges. Hence, this series n going 1 to infinity, -1 to the power n over n, is conditionally convergent. Okay, again, series could only be conditionally convergent if they have some terms that are negative, and that's certainly the case with this one. Okay. Okay, so next we get to the what we call the comparison test. So we're gonna start now a bunch of tests for convergence of series, tests for convergences of series, and this one is called the comparison test. So proposition 2.5.16. Okay. And what we have here is a series and another series. And if we see that one converges, the other one we can show converges, or if we see that one diverges, perhaps we can show the other one diverges as well. So it's useful both for convergence and for divergence. Let's see how. So let n b1 to infinity xn be a series, you know, and another one n going 1 to infinity of yn be series, but with a specific condition on the terms such that, first of all the terms here we're speaking about series of non-negative elements, and the xn terms are always bounded by the yn terms. So the yn series, in a sense, bounds the xn series, etc. So the statement is that if this y series, n going 1 to infinity, of yn converges, then so does, or let me actually write this in a kind of slightly, just kind of in an if-then way, in an implication way. So if yn converges, just I'll put it like that, if yn converges, then, well, the series summing up yn, then the series summing up xn converges. Okay. Now, I would actually like to just say that we can already say this is pretty much the claim. So this yn converges, this one converges, this one that's above, it means that xn converges, a series of xn converges. The other part of what's called the comparison test is nothing but the contrapositive of this statement. So again, if this was A and this was B, now I also want to write not B implies not A. So what I want to say is I want to say not B, and I'll put here what not B is. That implies not A. So I don't want to prove things twice. I just want to prove things for this statement, which we can call statement 1, and statement 2, which is just going to be the contrapositive, will just come from it. So what is not B? Well, not B means that the series with the smaller elements, or at least the elements that bound the other elements from below, the series of xn does not convert, diverges. Okay, so, and not A means that the series of the y's diverges. Okay. So there'll be no need to prove number 2, because number 2 is just going to be a consequence of number 1, because it's a contrapositive of number 1. But we could use this theorem in both ways. If we have an upper bound for each term and the series of upper bounds converges, great, we've shown convergence. If we have a lower bound and the series of lower bound diverges, then we have divergence. Okay. Now, since the kind of the crucial assumption is that all of the terms, both the xn and yn, are non-negatives. So partial sums are monotone increasing, because we're talking about series of non-negative terms. So the partial sum n1 to k in this case is also bounded by the partial sum n1 to k of the y's. Okay. And we're proving 1. So I'll just prove 1 again. 2 is a contrapositive. Okay. So since this series, the y series, n1 to infinity of yn converges, that's our assumption in 1, this thing, it is bounded. Well, sorry, the partial sums are bounded, right? The partial sums are bounded, again, by the monotone convergence. So what we have is that the summation n1 to infinity, n1 to k of yn is less than b, boundedness, if we speak about bounded sequence, you'd like to put an absolute value, but we're speaking about here about non-negative terms. So no need for the absolute value. And by what we had here already, that's greater than the sequence of xn's like this. Okay, the sequence of partial sums of xn's. Hence, sk, this sequence n1 to k xk, or this sequence, the sequence of partial sums, k going 1 to infinity, is bounded. And it is also monotone increasing, hence converges. That's it. So there was not a whole lot to the proof of this theorem. It's again just a great consequence of the monotone convergence theorem. Okay. Now, this theorem kind of goes hand in hand with a very popular series called the P series. And but it doesn't have to go just with that series, but it just go, the P series is a series we compare to a lot. And let's write this proposition 2517 P series. And this is one for which we'll skip the proof. I'll just say a few comments about the proof. So sometimes this is called the P series proposition or the P test. Okay. So for any number P is now a parameter. The series sum n1 to infinity 1 on n to the power p converges if and only if p is greater than 1. Okay. So let's see a few things about this. So first of all, if p here is just take p0, for example. Okay. So what is a series? This is sum n1 to infinity on 1 on n to the power 0. That's just the series of the constant ones. Right now, that's already, we know, does not converge because the general element does not go to 0. That is a necessary condition for convergence, right? Take p negative. So if you have p negative, okay, take p negative. So then the sequence 1 on n to the p, it actually, right, this sequence for n going 1 to infinity is actually an increasing sequence, right? So for example, if p is -1, then the sequence is just negative n. Sorry, is just n, right? So 1, 2, 3. Sequence increases. So again, it's not that it doesn't even converge to 0. It doesn't converge. So again, the series obviously doesn't converge. So for p is less than or equal than 0, this proposition is interesting, but not as interesting. Now take the case of p equals 1. That was the harmonic series, right? That's sum n1 to infinity 1 on n. That's a harmonic. And that was kind of a special series because, we saw that even though that this thing goes to 0, the series still diverges. We've pretty much proven that before. Okay. And what the proposition tells us is that for all p's, also in between 0 and 1, 1 inclusive, they behave like, even though this general term actually goes to 0, they behave like the harmonic series. Okay, so the series diverge. But what's kind of nice is that if you get to something that's only slightly greater than 1, so if you do sum n1 to infinity of 1 on n p plus 0 point, well, sorry, I'll just put 1 plus, I'll just put here, say 1.01, okay? Then this thing already goes to 0 fast enough and the series converges, and as you increase p, it will certainly converge. So that's the story. And just one more kind of thing to say about it is a very famous sum n1 to infinity and 1 on n squared. If you take p equals 2, then you get the famous formula pi squared over 6. So the series converges, and you actually have an expression for it in terms of the very well-known pi, right? So you can almost use this to, well, you can use this to define pi in one way or another. You would say that pi is 6 times square root n1 to infinity on 1 on, sorry, 6 times the sum n1 to infinity 1 on n squared, and then to take square root of that. And that's one way of getting pi, if you would like. Okay, you can try it yourself. Try it on the computer. Just add a few terms of the series, see that you get close to pi. We're not going to deal with how to compute this value. And indeed, in this case, series is quite special that the value is computable. I'll also say about the p-series that the Riemann zeta function, which is kind of very closely related with the Riemann hypothesis, which is one of the biggest open problems in mathematics, is really the function which is this series when you make it a function of p, of the argument p. So a lot to do with this series. Now, I won't show the proof here. I'll just say that the proof uses kind of arguments that are similar in nature to what we did with the harmonic series. We're speaking about the proof of, this would be the proof of convergence. Okay. So the proof of convergence for p being greater than 1 uses similar arguments to what we had with the harmonic series. Only that in the harmonic series, we show divergence. And here, what we're doing is we're not going to do a lower bound to the terms. We're actually going to find an upper bound to the terms. But you could look at the proof if you're interested. It uses kind of a similar computation and then a convergence argument. Okay, so that's for the case of p greater than 1. For the case of p less than 1, less than or equal to 1, all we need to do, well, for case of p equals 1 was proven, that's a harmonic series. But the case of p less than or equal than 1, all we need to do is we need to do a comparison test with the series 1 on, okay, with the harmonic series. And it will just follow from the comparison test because we'll see that the harmonic series diverges and the y-nth term is going to be greater than the x-nth term, and that's all. Okay, so that's it for the p-series. And so, yeah, the proof of the p-series, at least for the regime of p less than or equal to 1, use the comparison test in its own right, and the p greater than 1 is a bit harder. And then this allows you, of course, to look at many examples, as you will, and you probably have done this already in calculus courses, where you find a series where you compare another series using the comparison test, and you plug the p-series either here or here, depending on your needs. Okay, and that's kind of that's what you call the p-test. Okay. Okay, so the next test we'll visit, and you've probably dealt with such a test in a calculus course already, is called the ratio test. Again, we're not going to show the proof just because of lack of time and, just to save you time as well, but we'll just speak about the essence of it. So the ratio test. So in quite a few of the proofs, some of which we are omitting, the geometric series plays a key role because we often kind of do a comparison in one way or another to a geometric series. So if you consider, just before we get to the ratio test, just a side comment, if you consider a geometric series n0 to infinity r to the power n, and if you were to look at the ratio between the n plus first term and the nth term, Okay, so this is the n plus first term. This is the nth term, if you would like. Well, when I'm speaking here about terms starting from zero, so this is a term with n and term with n plus one, but that doesn't matter. The point is that this ratio is just a number r. And we already know for geometric series that if the absolute value of r is less than one, the thing converges. Otherwise, and if the for geometric, we also know that otherwise it diverges. But specifically, we also know if the absolute value of r is greater than one, it diverges. So this kind of analogy between the very well understood geometric series and sometimes you look at more complicated series yields a ratio test. So let's just write the proposition, okay, and understand what it says. So proposition 2.519, okay. So let the summation n1 to infinity xn be a series. And here we have the condition that xn is not zero for all n. Okay, because we're going to be dividing by xn. And assume, or let, or the precondition of the theorem is that this limit exists. So the limit n to infinity of the ratios of the absolute values of the terms. Okay. The n plus first and the nth term exists. Okay, so if you can't say anything if this limit does not exist. Okay, but that's kind of a precondition for this theorem, for this proposition. So if this limit of the ratio is less than one, that kind of puts us at the analogy of this regime, then the series converges absolutely. So it doesn't only tell us that the series converges, it tells us that it converges absolutely. Okay, so that becomes relevant if we have negative terms, the series converges absolutely. But again, when you say the series converges absolutely, what you know is that the series, this one, when you had absolute values, it converges. Okay, but you still just say the series converges absolutely. And the other direction, if L is greater than one, then the series diverges. Okay, the proposition doesn't say anything about L being one, unlike the geometric case where we understand the case of L equals one. So I'm not going to do the proof for the ratio test, but I'll just say that the key idea of the proof of the ratio test is to represent the series with a tail that is a geometric tail, or with a kind of that also compares it to the geometric series, and that kind of plays the key role. Feel free to look at the proof. Now, another somewhat similar test, and also here, just in terms of time, we'll also skip the proof, is a root test. And I assume that in a calculus course, you've used both the ratio test and perhaps the root test. Okay, so here is proposition 2.6.1, and that's a root test. So again, we're speaking about a series. And now we take L as the lim sup n to infinity of the nth root of the terms. Okay. So that's what we're looking at. We're looking at the nth root of the terms, the absolute nth root of the absolute value of the terms. Now this is the lim sup of that quantity, but if the limit exists, then the limit is just a lim sup, right? So you could, if you want a version of this proposition without a lim sup, without a limit superior, without the upper limit, well, sorry, without limit superior, I should say, not upper limit, forget that phrase, then, if the limit exists, you could have just had the limit, okay? But if it doesn't exist, then we get a slightly stronger theorem because it also uses the lim sup. So again here, if L is less than 1, then we again get, just like in the ratio test, we get converges absolutely. And the other case is when this limit or lim sup, if you would like, is greater than 1, then the series diverges. So if you if you think about the root test and the ratio test, they both look at some sort of limiting quantity associated with the general term of the series. The root test looks at the nth root of the absolute value of that term, and specifically looks at the lim sup of that, of the limit superior. Again, if the limit exists, the limit is enough. And if this thing is less than 1, you've shown convergence. If it's greater than 1, you've shown divergence. And the series test does the same thing, only here we have the condition that we cannot divide by 0. Sorry, did I say the series test? The ratio test. Okay. So that was that root test. And I'll just say again, even though we're not looking at the proof of the root test, I'll say that the geometric series plays a crucial role there. Okay, so this puts us at the final criterion for convergence that we'll speak about, and this one is called the alternating series test. Okay. In contrast to the root test that gave us absolute convergence and the ratio test that gave us absolute convergence, this alternating series test is a good way to generate, if you would like, examples of series that are conditionally convergent. So it'll be clear when you see it. So this is proposition 262. Okay. So let xn be monotonic decreasing with xn greater or equal than 0. Sorry, xn strictly greater than 0. And limit n to infinity of xn equals 0. Okay. So xn is something like 1 on n, or it's any monotonic decreasing sequence of non-negative numbers. Okay, strictly positive numbers, actually. Strictly positive number. So then the series -1 to the power n times xn, okay, converges. Okay. And sometimes it might conditionally converge depending on what we do. So that's the proposition. So this is kind of a boilerplate series where you just need to have a sequence that this is 0, and your sequence needs to be monotonic decreasing but strictly positive, and your series adds a term, subtracts a term, adds a term, subtracts a term, adds a term, subtracts a term, adds a term from that sequence. That's what I mean, from that original sequence xn. Okay, and that series converges. So immediately by this alternating series test, this example that we spoke about here, this series, right? So here the xn is 1 on n, and then that is that type of series. So we see that it converges by, if you believe this proposition state, the alternating series test. But that is a case where it's conditionally convergent, because its version without the sign changes, namely the harmonic series, diverges. So it's not absolutely convergent. Okay. And again, due to lack of time, I'm unfortunately just going to skip the proof. But for this one, I recommend reading it. So read proof um, at some point. Um, page, it's a one-page proof on page 101 because it's a neat proof and it also has kind of uh, analysis arguments that are kind of useful. But we're just going to skip it just to move on to the next thing and to close this unit quickly. Okay, the final topic we're going to just very briefly touch, but it's kind of conceptually, it's a bit of a neat topic and an important one. So we will just say a few words about it, is rearrangements. Okay, the rearrangements. So of course, if you have a finite sum n going 1 to say k of xn, then by commutativity, you can do x1 plus x2 up to xn, but you could also do x1 plus x7 plus x4 plus do some any other order that you'd like, as long as you finish someplace x65 and maybe xn where some is here in the middle, and that's all fine. So you can rearrange the order. But when you come to a series, it's a different thing. It's not a finite sum, it's a limit of a sequence, and that sequence was a sequence of partial sums. And the next element of the sequence of partial sums always has this one next element that you add in. So it's not exactly clear if you can do rearrangements of series and not change the both the convergence or divergence property of the series and its value. Okay. So the way we deal with this in terms of series is we say we have some function sigma from the natural numbers to the natural numbers that is bijective. So it is a reordering of the numbers in one way or another. It's a way of shifting the indices, but for every natural number, no matter which natural number you give me, there is a resulting natural number that you get as the output of sigma. Okay. So given the series, and bijective means it's one-to-one and onto. So there's a one-to-one correspondence between the original series, which is sum n 1 to infinity of xn, and we get, given this one, we get the series sum n 1 to infinity of x sigma n. Okay, so this sigma here was kind of the switched order, if you'd like, the rearranged order. Okay, so that's a rearrangement. And the key result that we get with rearrangements is that absolute convergence keeps us safe. So this is the proposition, and I'll skip the proof for this proposition, again, due to lack of time, but it's still an important one to see. So let the sum n going 1 to infinity xn be an absolutely convergent series. Okay. Converging to L. Okay, L is the sum of the series. Let sigma natural numbers to natural numbers be a bijection. Then the rearranged series with that bijection, whichever bijection you would like, whichever rearrangement you would like, as long as you've got all the terms in there, but in a different order, is absolutely convergent as well. And converges to L. Okay. So what we see is that this notion of absolute convergence of the series, okay, so that means that the series sum n1 to infinity of the absolute values being convergent puts us on a pretty strong footing in the sense that the order in which we throw in elements to the partial sums never matters in the sense that it does not change the um, convergence or divergence property of the series. It does not change the limit or the sum of the series, if you would like. Okay. Now, in particular, if you're speaking about a series of non-negative terms, okay, then if it's convergent, it's always absolutely convergent. Okay, so when you're speaking about series of non-negative terms, or even strictly positive, if you look, but certainly non-negative is also good, then rearrangements work fine. Okay, and I'll finally say, just as a point, that so I'm not going to say this is a theorem or anything like that. I'll just say that note that for conditionally convergent series, this proposition does not hold. So you can't strengthen the proposition for that. And in particular, what you can actually do, and that's quite fascinating, feel free to read about it in page 103 of the book if you'd like, is you say you start with this conditionally convergent series that we've already spoken about, the one that you get from the alternating series test. Okay, so this one, which kind of looks like the harmonic series, but it's with positive, negative, positive, negative, positive, negative. It's conditionally convergent. So in particular, this series can be rearranged so you can sum the terms in a different order in this one to obtain any limit L in R. And that's quite fascinating. But that's just the way it is. So the order in which you sum terms in conditionally convergent series in general matters a whole lot. Okay, so this is all that we wanted to say about series and this kind of series of makeup lectures. We didn't speak about multiplication of series, and we didn't speak about power series, and we just skipped a few other results and proofs. But this should give you a general sense of all there is in this, sorry, not all there is, but a sense of kind of the key aspects of this important topic that kind of generalizes sequences or looks specifically at sequences of partial sums and has a lot of structure. So good luck. Bye-bye.